Chris, can you send me a private message with your phone line so I can know which line to unmute and connect with you? Great. So I guess we are ready to go whenever you all are.
Okay, are we ready? Can you hear me?
Yeah, I can.
Yep.
I can hear you.
All right. So it's my pleasure to introduce David Robinson from Rutgers University's Department of Geography, and he's New Jersey's state climatologist. David's climate system research interests range from global to local, and the majority of his research has focused on hemispheric and regional snow cover dynamics and interactions of snow cover with other climate elements. This includes maintaining an internationally recognized database of northern hemisphere snow extent throughout the satellite era, and that's at snowcover.org. And this information is used in his global snow labs research, efforts of others, and his extensive contributions to national and international climate assessments, including the most recent IPCC report. And with that, David Robinson.
Great, Chris, thanks very much. Thanks to you, Emily, and Jessica for getting this all set up. It's a pleasure to be speaking to all of you, wherever you might be. Topic today is something near and dear to me, something I've been doing for many, many years, and that's looking at snow cover extent, large-scale extent over primarily northern hemisphere lands. We'll talk a little bit about snow cover over Arctic sea ice later on in the presentation. But the focus today is on large-scale and snow cover extent. And with that, we'll start moving through the slides. Except I can't get it to advance. There we go. Where we're headed in the next 40, 45 minutes or so, go look at why snow cover. I think I'm probably preaching to the choir here, so I won't spend too much time on that. Something on the 50 years, almost 50 years of satellite snow cover monitoring. What does the record show after almost 50 years of monitoring large-scale snow cover over northern hemisphere lands? And talk about a climate data record that has been assembled, soon to be available, that not only looks at snow over land, but also snow over ice. And then with whatever time remains, and I've thrown in a number of slides towards the end that we very well may not get to them all, but they give an example of just how we're using these large-scale snow cover database in this day and age to study different problems associated with the climate system. And those slides will, of course, be available up and online following this presentation. So we'll see how far we get there. Oh, and I also don't want to fail to mention that the majority of my research on snow over the years recent years, has been sponsored by NOAA and by NASA, years back, NSF as well. Have to start with some sort of a snow cover image, and what better place to start is near home, centered on New Jersey, but including much of the Northeast. This is actually from 4 winters ago, which was that massive snowy winter from D.C. To Washington. As a matter of fact, here you actually see very, very deep snow cover over the mid-Atlantic states. You can see the Great Valley through Virginia up into Pennsylvania into the northwest corner of New Jersey. You can look south and see the New Jersey pinelands, where there is plenty of snow cover underneath the trees. But interestingly enough, if you have a high enough resolution, you can see up here in the Hudson Valley there's actually areas that are pretty much absent, devoid of snow cover in that very snowy winter. You can see a brownish hue there. If you looked at enough of these images over the years, which trained meteorologists do to create the very best hemispheric snow product, you become very skilled at determining snow, free land, snow-covered land, and of course in an area like this, just over the southern end of the Finger Lakes, cloud cover. Moving on. Here's a quote that I found years ago that I've probably shown too many times in talks, but I enjoy it every time I see it. All that pertains to the covering of snow on the ground is so great importance for science that it ought to be observed and published in detail. I think every funding agency should see this. It was by a Russian geographer named Voykov in the Quarterly Journal in 1885. So some things just never change, do they? But a quote that I love to show to a variety of people. All right, moving on. Why? What's the big deal about snow? And again, as I said, I'm telling many of you things you already know. But there you can see a list of how you could put a snow-covered data set, a climate data record, if possible, and we'll talk about climate data records a little further on. But there's so many valuable things, including the hydrologic aspects of things, for monitoring, assessing issues, estimating runoff, and so on and so forth. And we're below what you see is just an example of groups that have contacted our snow lab here at Rutgers, and no doubt many at your institutions, or some of you listening in and watching this. Just so many different entities have an interest in knowing where the snow is sitting, of course on basin-wide scales, but here we're talking on larger scales, either large basins or even broader, things of that nature. And you can see the various the research groups for education, the international aspects we have, and the number of reports and assessments that we're very pleased and honored to be able to participate in or contribute to. Okay, so we've got this 50-year record of snow, and there's a lot of different ways of looking at snow at the large scale. There's been some wonderful work with microwave data over multiple decades, and with the MODIS snow products of the last decade and a half or so. But as I say later, the real workhorse over the satellite era has been this product produced by NOAA. It was in their produced in their satellite application branch until the late 90s, when and then it changed. Even the format of the maps changed, and then it was shifted in the early part of the last decade over to the National Ice Center, a joint Navy, NOAA, Coast Guard entity. But this timeline at the bottom gives you a little idea of how things have changed in that department. These earlier maps in the 70s, you can notice the pen lines a little bit thicker, broader areas. Some of these numbers, by the way, early on, they put down numbers based on the brightness of the surface as it was recognized. That went by the wayside in the early 80s. By the time you worked your way into the 90s, just at the very end of the era when these charts were produced on a weekly basis, once per week, the pen lines have gotten smaller. There's a little more detail within the edges of the snowpack, but to a first order, they were prepared in a similar fashion. And then we transitioned over into the new era of the IMS, the Interactive Multisensor Snow and Ice Mapping System, again done on a computer screen now, but still the general manner in which these charts are made, be it in the past on a weekly basis or today daily, is that you have trained analysts who look at a variety of satellite imagery, and you can see below the variety of polar orbiting satellite imagery as well as geostationary imagery. Some of it can be looped in this day and age, and they produce these different these maps based on a variety of the satellite imagery. They look at the images. They put down where they think snow is sitting on the ground, where they see it's snow-free. And if at the end of a day they don't see the entire surface, you look back until the last time the surface was recognized as being snow-covered, which generally is a function of clouds obscuring the surface on any given day. And in the higher latitudes, solar illumination being down. Generally, once the ground is snow-covered, you lose your sunlight, and you can see that in the 1973 image. So while not constructed absolutely consistently, of course, during the last almost 5 decades, the general practice of this trained expert looking primarily at visible satellite imagery of various types, putting this into a map, be it in hand map or a computer-generated map, has remained consistent through time. So in many respects, you could say this is the longest, relatively consistent, satellite-derived environmental data record available out there. Again, changed some through time, generally consistent. As a matter of fact, when the transition went from the weekly to the daily charts and the resolution of the spatial resolution increased, we here at Rutgers got some money to study that transition and tried to smooth things out and maintain as best a consistent record as possible. And to this day, we generate daily charts at a coarser resolution than the IMS daily, but also we produce a weekly product to maintain that temporal consistency with the pre-daily era, with the weekly era. And we'll see some of that in just a moment. I should have shown this earlier, and excuse me for some of the words being cut off. This is the IMS system. We're now in phase IMS 2. There'll be an IMS 3 released in the near future. It's not going to be a big difference to anyone looking at it in particular. But you can see all the sources, the satellites that go in, the analysis at 4 and 24 kilometers today, and produced at the National Ice Center. So kudos to those individuals at NIC who are producing this daily product. Just briefly, I wanted to go over the fact that mapping snow cover extent is not all that easy. I alluded to that when I showed the first satellite image with the cloud cover, the partial snow cover, and the vegetation that can mask the snowpack. These images are actually taken in the winter of 1983. You can see a Cessna aircraft there at the top of the image. I was actually doing this at Columbia University at Lamont Observatory for my dissertation, looking at the surface albedo of snow-covered lands. And we flew a prescribed route over southeastern New York, northern New Jersey. And in these cases, we took fisheye photographs of the underlying surface from this one wingtip, and the other wingtip had radiometers mounted on it. And to the left is a bright snow-covered field with over a half a meter of snow on it, and the albedo of that field was 0.8. To the right, it may look a little bit brighter, but there's deciduous forest, and interspersed within that are pines, and that albedo, despite the same depth of snow cover, is at 0.25 or 25%. And these are the differences. When you're charting snow cover from a satellite image, you might very easily pick up where the snow sits in that image on the left, but it can be a more taxing issue to do so with the imagery, with the surface conditions on the right. This is something, again, only 2 dissertation images, I promise. This is something from dissertation where I looked at the maximum brightness of all snow-covered lands over the northern hemisphere. This was used quite a bit in over the decades for a variety of applications. But the areas in darker blues are where it's very dense forest, boreal forest, often made it difficult to ascertain whether there was snow cover or not because of the density of the forest. To the south were steppe and prairie, and to the north, taiga and tundra in the red, showing you that the albedos were much higher under maximum snow-covered conditions. So this is something an analyst making these maps would have to be familiar with in order to help them train them to identify potentially snow-covered or snow-free surfaces. And it becomes tricky in place. Here you see same date, two different images, two slightly different areas. One with a fresh snow cover, and that is the 2003 image. In the lower right, the 2007 very patchy, thin, older snow cover. And you have to recognize that these charts that we're talking about here are binary. It's snow or no snow. The more modern MODIS method of tracking snow cover tries to look at the fractional coverage within a grid cell. But with the NOAA, the long-term lengthy record, it's a binary system, snow or no snow. And again, this shows you a progression of melt over the same field over a multi-week period of almost a controlled experiment of melt back there in that 83 event. A melt that proceeded with temperatures above freezing during the day, below at night, little to no precipitation over about a 4-week period. And you can see how the full snow cover to the top image with a tree in the middle of that field begins to open up, and then even get a sense of drifting that occurred around that tree. Now, we didn't have GPS at that time to align things, so it's not perfectly aligned on these images, but you get the idea that there's snow cover and there's snow cover and there's snow cover. And is it because there's a masking effect of vegetation, or is it because the snow cover is patchy, why you don't see the surface quite as bright? And this is something that certainly has implications in terms of how much water might be locked up in that in that snowpack. This is an image from yesterday from the MODIS satellite. This is, I think I grabbed this from the Aqua afternoon overpass. And on this you see a variety. First of all, you see the record frozen Lake Michigan and Superior. But you can see snow cover throughout Wisconsin into northern Illinois. You can see Chicagoland right here, where it's a little bit darker feature. Here you can see some streaks of snow cover as the system came through. And even to the south, you can see some evidence of snow cover. But I might also add there's some cirrus cloud in here as well. So this is the training, and this is the trickiness to observing snow cover using visible satellite imagery. Okay. Then there's the ground truthing. We've tried to do ground truthing over the years. To be honest with you, there hasn't been enough. This is just a week ago here in New Jersey, the northern half of the state, snow covered, and quite a bit of snow cover. You go from essentially no snow cover here in south central New Jersey, and you can identify that from the observations on the ground, to a 6-inch to 1-foot snowpack, but literally just within miles here in central New Jersey. And I might attest to the fact that this snowpack right here is more like fern than snow. It has a water equivalent of 2+ inches, and the snowpack up here today has an equivalent of 3 to 4 inches of liquid in it. It's been quite a winter. And I might add, for those who don't know, CoCoRaHS stands for the Community Collaborative Rain, Hail, and Snow Network. This is a network managed by terrific folks out of Colorado State University, but it's national. Here in New Jersey, we have roughly 300 active volunteers who on a daily basis will report precipitation we're fortunate to get over 200 observations in any given day, and admittedly fewer measure snowfall, or in particular snow cover. And later on I'll show you an image of some that actually go out and measure snow water equivalent for us as well. Very useful ground truth that's only begun. The CoCoRaHS program isn't that old. Goes back 15 years in Colorado, but less than that other places nationally. And that's really valuable data to team up with co-op observing data to do some good ground truthing. Here's some other pretty good ground truth. Case where the maps, the analysts saw snow in Algeria and put it on their map, and a colleague of a colleague sent along some data showing the snow in the Algerian desert. This is what we do on a daily basis. We grab the higher resolution satellite data and we put it into the coarser resolution. We have enough years of data on a weekly basis that we've come up with a daily climatology. We difference that, and the chart on the right is the departure. Anything in red should have snow cover on January 10th and does not. And with the blue, it should not, but does. And we do this on a daily basis. As far as I know, our website, snowcover.org, that you keep seeing in the lower right of the slides, is the only site where, not where snow cover can be found. The National Ice Center, you can see the higher resolution maps. It's the only place where you can see departures on a daily basis. And this just shows you what we do on a monthly basis. And there we do have percent cover based on a weighted weekly product. And on the left, you can see the frequency of snow cover over the course of the month. And I'm sorry, I left the scale off there. Dark blue is 90 to 100% cover, and it grades down to a much smaller fraction of cover. And on the right, you've got the departures for the month of January 2012. The earth tones, below average snow cover, the blues above average. These are available for every month back to 1967 on the website. This shows you the actual map produced, and you saw one earlier, at the higher resolution for the IMS. And as I say, you can do some interesting things here. You can look here at 2011 with a very broad extent of snow, or look just a year later and see how very little snow cover is over the lower 48. And here's the average January extent. Just we do have climatologies as well as just individual years available. And again, it's not just the maps. We have the digital, obviously we have the digital data as well. And then you just go to another year, and this is one of those cases where snow touched portions of every state on this particular day in 2010, even snuck into northwest Florida. And I recall seeing an image, a photograph from the top of Mauna Loa showing some patch of snow on Hawaii. And here's a little ground truth taken by a colleague, Tom Moat, down at University of Georgia here in Athens that day, confirming their southeastern snow cover. And then sometimes we'll difference this. This is a map I generated for an annual snow piece I write on snowstorms of the past year for WeatherWise magazine each year. And this one just came out. And on it, what you can see is the difference between the last two Marches. The areas in yellow had snow cover in 2013 on the 25th of March, did not have it in 2012. The areas in gray had it in 12 and not 13. And the red line is the average March 25th snow cover. So you can see the very warm March of 2012, the snowpack had receded well up into Canada by late March. Last March, which was a below average month, the snowpack sat much further to the south. As a matter of fact, this week, the snowpack, you may have seen this in the paper, the snowpack earlier this week was the third most extensive for this late in the season with that storm that last weekend tracked along the southern tier of states and brought snow cover to the panhandle of Texas, Oklahoma, and down into the southeast. So 2012, markedly different than this March and last March. It's just, again, just shows you, I'm going to quickly go through these. Already really discussed these. So let's get on to the snow cover record. What does it show? What's been going on snow cover-wise in the last 4 or 5 decades? And this is a climatology. This is just based on multiple decades of record. You can see by month the millions of square kilometers, how much snow lies over northern hemisphere lands, including Greenland, and the contribution to that cover from Eurasia and from North America. Very simple climatology. Of utility to climate modelers at times to see how well their climate models are doing the gross climatology of the northern hemisphere. These maps show it in a little more detail, what the normal climatologic coverage is in the months of January, April, July, and October. Clearly, when you get into July, you're talking about some scattered mountain regions, perhaps portions of the archipelago, Greenland, let's not forget a little bit down here in the Himalayas, but essentially most lands devoid of snow, as opposed to January when you can have upwards of 48 or 49 million square kilometers of northern hemisphere lands covered by snow. One of the most notable variables in terms of its extent from one season to another. But what about changes with time? And this figure gets a lot of exercise. This appears in the Bulletin of the American Meteorological Society's annual report and has been used with the IPCC. And what you see here are 12-month running means of snow cover extent over northern hemisphere lands. The solid line is northern hemisphere, the red Eurasia, and the blue North America. And with these, you can see these are departures, I should say, running means, departures, and you can see some variability over multiple month phases. Remember, these are 12-month running means, but you'll see here in the mid to late 80s almost a stepwise change to a different regime, a very low one in the early 90s. Then it's fluctuated up and down, and in recent couple of years been closer to the long-term mean. And sometimes you can see the two continents, the western and eastern hemisphere, somewhat in lockstep. Then you get other periods of time when there's a difference here between North America and then Eurasia up here. Generally, Eurasia drives things, given it's the larger landmass. But these are departures from the long-term means and something worthy of quite a bit of attention over the years. But again, that doesn't tell the whole story. This is an annual average, and you'd like to know what happens seasonally. And this is a very broad first look at seasonal anomalies. Orange fall, blue winter, green spring. First thing that's drawn to your attention, I suppose, is winter doesn't have particular percent anomalies that are large. The larger anomalies are in the swing seasons. And for fall, it's been up and down. And actually there is some discussion now, a paper by a couple of Canadian colleagues, Dirksen and Brown, which suggests that as we've gotten into the IMS era, analysts may be more readily able to see snow cover on the ground and resulting in an overcharting of snow in the fall compared to past decades. I'm not so sure. I think they can also see gaps within the snow cover as it develops in the fall. So this is an area that warrants some additional study. But of course, the key story here, and the story I've been writing about since it was first identified and we published it in Geophysical Research Letters in 1990, was this decline in spring snow extent. Each decade having less snow in the spring than the previous decade. And again, there's been another paper by Dirksen and Brown that looked at this, concluding that maybe the charting is being a little more detailed in recent years, and the snowmelt is being identified a little bit easier with satellite animations and such, but that the conclusion of their paper was that there is no question that the general trend is absolutely robust and significant. So let's move on and look at a little bit more detail of the spring. This is your year-to-year evaluation of the spring, and as expected, there is quite a bit of variability from year to year. This shows you April time series, departures from the mean, and you can see that in April 13, the last year of record, first one well above normal in a couple of, well over a decade. This is where the positive anomalies were found over the north central U.S. and Canadian Prairie and parts of East Asia. This looks at May. May, we've seen a significant decline in the Northern Hemisphere, particularly in Eurasia, somewhat so in North America. And note that this is not commensurate with the start of the IMS era. The IMS era began back here. So later on we'll look at the first half of the IMS era versus the second half. So this is not a function of the changing to the daily high-resolution product. There is something real out there that is happening that's resulting in significant decline of May and, not surprisingly, therefore, June snow extent. This just shows you May of last year on the right, the earth tones being the negative anomalies during the month of May. May was a record low last year, I should add, over Eurasia. Over North America, the record low was in 2010, and on the right is what it looked like, rather average, in 2013 in May. Here's a look at June. You see very little snow left on land over the course of that month because it's melted off in late May. Then we broke this IMS record in half to see what was happening. The first half of the IMS era, if you will, the second half. And we plotted it daily from March through July. And you can say early in the season, both the early part and the latter part of the IMS year are very similar. But they began to diverge right in the middle of this melt period as you got into May and June. And the early era was showing more snow cover than the last 8 years. Looking at that, where did those differences occur? And they're not huge if you look at them. In March, of course, there wasn't much of a difference. And that's quite evident from looking at this image where both are shown in dark blue. And you can see the colors that appear if it was there in the first half of the era and not in the second, or vice versa. When you get into April, there's beginning to see a change with more of the brown there, meaning less snow in the second half of the era than in the first half. You'll see that in the middle of May, as well as the middle of June. So these aren't enormous areas, so we have to be very careful when we come to conclusions, but they all point in the same direction. So there's a high degree of confidence that we are seeing a reduced spring snowpack, particularly in the last 8 to 10 years. Moving on, What are we doing to put together the best database for all of you folks listening in, perhaps, and others to work with? And this is a project funded under the Measures effort of NASA. This project is coming to an end, and in it we've been developing a climate data record, or what NASA calls an environmental satellite data record, of snow cover not only on northern hemisphere lands but also on sea ice and the Greenland ice sheet. Our goals were to assess the current products and to fuse records together. And you'll see in a minute just how we've done so and how they will be available through the National Satellite, the National Snow and Ice Data Center, the DAC at NSIDC out in Boulder. Climate data records are known for having length, consistency, continuity, and good documentation. If you want to learn more about that, there was a National Academy of Sciences Research Council publication on that 10 years ago. I had the pleasure of chairing that committee. And here is our methodology. We grab data from a variety of sources. We spruce up the individual products. We grid them all to EASE-2 format. We develop essentially a GIS layering system. We aggregate them, and they'll be available as NetCDF files and be very well documented. This is an idea of what the fused continental product looks like, and what you're looking at here is the hemisphere on day 32 of 2006, and this scale here shows you the availability of the different products in some cases, or where they all coincide. For instance, by all three products, I should say, one is a microwave product of Snow Extent by Tom Mote at the University of Georgia, a NASA MODIS cloud gap filled snow product by Dorothy Hall at NASA, and then the NOAA IMS product produced at the National Ice Center and cleaned up and archived here at Rutgers. And this gives you some confidence that all three are showing it, and that's pretty great. Your confidence may decrease as certain products show snow and others don't. This is a pretty coarse resolution, so it's a little difficult to pick out all the details. We're also using a common BU, Boston University MODIS Land Ocean Coast Ice Mask to this, as well as when we merge it with the onset of snowmelt on sea ice, a product produced by Mark Anderson at the University of Nebraska, the onset of snowmelt atop sea ice. And then we've also thrown in, it's a long story I won't get into, something on sea ice age that's produced by Mark Sudi at the University of Colorado. That's part of it. And we also use Walt Meyer, who was at Snow and Ice Data Center, now is at NASA Greenbelt. We use his sea ice product for the extent of sea ice as part of this exercise. And then Tom Mote at the University of Georgia has looked at Greenland surface melt, kind of the melt condition of snow atop the Greenland ice sheet. And that is another product. Again, they're all going to be in the same data set, the same resolution, EaseGrid product, NetCDF availability. And we're kind of, if you will, erasing the boundaries between land and ocean and ice sheet to look at snow cover on a continental basis. And these are the fused products that will be part of the project, and their spatial temporal range, their spatial resolution, coarser over the long term, the components that go into the product, no MODIS in the longer term data set, for instance, and their temporal resolution. So I won't bore you with looking at that table any further, but these are the products that will be available to the public. We're finishing up this project later this year. These will all be available. If you have any interest in them now, please contact me, and we'll see what we can do for you. Finally, in just the last 5 minutes or so, as expected, I knew I wouldn't have a lot of time to get to this, but I wanted to give you an idea of just how we're using this large-scale snow extent information. And in this case, Ross Brown, aforementioned Ross Brown and myself, we've done this for the last two IPCCs, looked at the satellite era of snow extent using the satellite image products, but also looked at station observations to try to get a feel for how snow cover behaved, if you will, in the springs in the pre-satellite era. And the conclusions are that snow cover has decreased significantly, as it says on the bottom, since 1922, and that rate of loss has increased in the last several decades. So one example of, attempting to merge station observations with satellite product to look at the long term. Then, always of interest is, how does the snow cover jive with temperatures? And what you see here are the May snow cover anomalies for North America and Eurasia, where you can see, for instance, Eurasia below average snow extent. And here are the temperature departures, and you can see the link between the departures of snow and relationship with temperature. Here, a colder Alaska in May, a colder Alaska and a more persistent snowpack. Again, this is nothing surprising, but it's something that warrants, I think, further study on the larger scale. And one may ask, which is leading which? And of course, the answer is yes. We've got it's cold because there's snow, and there's snow because it's cold. One of my graduate students is working partway through a dissertation that's trying to look not at anything in the time series format, but what is initiating melt in these areas. And the answer, of course, is sometimes it's a local forcing of more thermodynamics on a local basis. Other times it's been more atmospheric dynamics with advective fluxes doing so. And it can vary from year to year in a given location, and we're beginning to find locations where there's a stronger signal of one over the other over multiple years. Here's another example. Stay long on that, just pointing out here one of the colder areas in the spring, that negative anomaly in June jiving quite well with a warm thermal anomaly. This is, on the hydrologic side, this is some work led by Dajing Yang, was at the University of Alaska, now he's with Environment Canada, and also managed the CLIC program for a while for WMO. And I worked with Dajing along with several others from the National Snow and Ice Data Center, Richard Armstrong, Mary Jo Brodzik, for instance, and looked at a very coarse scale at large river basins and just how they responded, how discharge responded to snow melt. And here you can see just snow extent over this period in 1999 over these basins. The gold is snow cover, and you can see the outlines of the basins. And this is the relationship of the loss of snow cover within the three individual basins and the discharge in the Ob, Yangtze, and Lena basins. And, you know, in some respects, we were pretty surprised that we're only looking at snow extent here. We're not looking at SWE, yet there was a very powerful relationship between the two over these large-scale basins. We then took the study and used some data on SWE from microwave products, and this is the Colorado group did a fine job producing this. And we know we don't have time to talk about the pluses and minuses of looking at microwave data of snow extent and trying to glean a water equivalent from it. But I think you'll be convinced that on the large scale, it's quite impressive. Here again, you can see the snow melting back according to the microwave data. And here you see the weekly SWE estimated in the basin. And notice we've got the reference to these papers here on each of the slides. And this is the discharge from the basins which jives quite well with the loss of snow from them. I don't have one figure that combines them like with the snow extent. But to a first order, they do a very nice job on this kind of large basin scale. Again, some ground truth. I promised this before. This is back in that winter, very snowy winter of 2010, with the southern half of the state of New Jersey having more snow than the north. And these are the volunteers who measured SWE over the course of that one particular day. I dare say this is unprecedented to have this number of SWE observations available for ground truthing over this large a scale. So there's a tremendous value to what's being done by these CoCoRaHS observers out there. It's not perfect. We all know how difficult it is to measure SWE, but it's a very valuable input that the Weather Service hydrologic branch just covets when looking at potential flood threats in the spring season. This is some work done by Gina Henderson, former postdoc of mine, where she's done a PCA analysis of snow cover extent cycle, finding some, sorry, this figure shifted a little as I redid it for here, but a lot of the variance explained by the first three components in both Western and Eastern Hemisphere, and nice seasonality between the components as well. Went on to look at the more extreme years of positive and negative sense, and you can see where the coherent regions are, and this is looking at North America's PC, but plotting anomalies in both hemispheres, both Western and Eastern. And then looking at relationships with sea level pressure, air temperature, and 500 millibar heights. And then looking at correlations of NAO and PNA. Again, no time, just want to give you a taste and invite you to look back through these for some more information. A postdoc, partially of mine at Rutgers, just finishing up, Debjani Ghatak, she's done an SVD analysis, let me click to the next slide, and found an interesting relationship between the loss of sea ice in the Arctic in the late summer and anomalies of fall snow cover. Again, work in progress. This has been published in JGR, and there's some other work at hand involving a variety of individuals. So I invite you to look into that. This is some work done by Judah Cohen at AER, looking at Eurasian snow cover in the fall and its relationship to the North Atlantic Oscillation, or the Arctic Oscillation, in the subsequent winter. Some of you may be familiar with that. Some work done by Environment Canada by Chris Dirksen, basically looking at models, CMIP models versus Arctic snow cover, and finding some discrepancies later in the melt season with the observed melt far exceeding what the models might expect. And with that, just sum up with just a few things. Why it's important to know where snow lies. It's a big part of the climate system. It's a very useful means of monitoring climate variability and change. I said a lot about the NOAA snow cover extent maps, the real workhorse over the last almost 5 decades, and the valuable contributions from other satellite sources as well. We've looked at trends in Eurasia and North America. Not so notable in fall and winter are trends, but certainly in the spring, in particular late spring in recent years, have we seen a decline. And then I introduced you to that new CVR that's coming out that will look at snow over all different surfaces and will soon be available. And then again, to repeat what was shown on an earlier slide, putting that large-scale snow extent information to work. Again, I invite you to visit the Rutgers Snow Lab or contact me with my email contact, and I'd be happy to talk to you when I'm not cross-country skiing, on, as I've had the opportunity to do many times this year, as today is our 62nd day of snow cover, the 45th continuous day of snow cover here in good old central New Jersey. with that, I thank you very much for joining the conference, and I guess we'll open it up for some questions.
Okay, I'd like to thanks a lot for your talk, Dave. That was great. I would like to remind people to go ahead and type in the questions in the chat box, and we'll try to. I'll give them to Dave, and then he can answer those as they come in. I have a quick question while we wait for some of the other questions to float in. I'm kind of like thinking over time in like the boreal forest and thinking of the forest-snow interactions that you've been looking at. And you know, over time that the areas that have burned in the boreal forest have actually increased. And I was wondering if at what level would those show up, if at all? Because you'd expect that if a forest area burned that you get more light in the spring and maybe that would melt out earlier. I mean, what level would you actually see those showing up in the data, if at all?
Well, that's a real good question. At 4-kilometer scale, you might be able to start seeing that. I think it would take a long period of time to reach any level of confidence that we were seeing any type of change. That's something more attuned to a high-res field study.
Right.
But, you know, things like that, burned out areas of higher albedo, the work that folks have done looking at more bushy vegetation in the Arctic tundra and how that may affect the distribution of snow. You know, there are changes going on up there for one reason or another, natural or anthropogenically induced, we don't know. But I think in many respects it's subscale to the level I've been talking about today.
Thank you. So I have a question from Jessica Lundquist. What would you say is the greatest challenge or source of error in determining a snow-covered area?
Boy, you know, it goes kind of three ways, because immediately what comes to mind, well, solar illumination, but I think that's okay. But one could hypothesize that if we start losing more snow cover, or the snow season starts later, we may have illumination problems with seeing the snow in the visible imagery, but we have the microwave to turn to. Snow cloud discrimination is awfully difficult. That is helped along with animations, hoping that the snow cover isn't changing as fast as the cloud cover might be, and which is almost always the case. And of course, the higher resolution and the animations help there. And then there's always the perennial problem of being able to see snow in forested areas. But I think probably of those, the greatest challenge remains cloud cover. And not just with and you could say we could rely on the microwave data, but the trouble is as the snow melts and the snow gets wet, it's no longer recognizable in microwave products. So it becomes a real problem in the spring if you're having extended cloud cover, that you may not be able to see the snow declining either in the visible or in the microwave portions of the spectrum. So that's probably the greatest issue in the spring with wet snow and cloud cover.
Okay, we have another question from Peter Kirchner. Have you looked for correlation between snow surface albedo and earlier snow melt? Yeah. If you're looking at the radiative dynamics of the area and you keep your surface albedo higher, you're going to have on a local basis less energy available to melt that snow. You can do even the back of the envelope kind of studies with that, and I did a couple papers in the 90s over Alaska looking at that, and actually my students beginning to look more at that. And you know, to a first order, that is going to have an important local impact, but there's so much more that comes from external sources or forcing as well, that it's difficult to sort out what's a local driving influence versus one that might be advected into the area. You know, as bright as that snowpack may be,
compared to an adjacent area that, say, is snow-covered, it still could be influenced by advective fluxes that will help to melt the pack. But all other things being equal, that brighter surface, a brighter landscape, should melt later and slower.
Okay, and another question from, this one's just a number, but what would you say about the GCM model's SCE, snow-covered extent, prediction?
Yeah, I'm not sure exactly what particular model that is. Was that GCM or G?
Yeah, it just says GCM models.
GCM, okay. Yeah, the GCM models, we've done a little bit of work, Alan Fry and myself, back with the AMIP-1 and AMIP-2 periods. So it goes back a ways now, looking at these GCMs. And the biggest problem, and it got much better between the AMIP-1 and AMIP-2 runs, was they held on to snow too long in the spring. There was just something in the workings of the models where it was holding on to snow too long. So to a first order, they did a good job with the distribution of snow over northern hemisphere lands. But the big problem, and it did improve between the first and the second experiment, was in the spring with their handling of snow loss. So again, pretty good, but some difficulties seasonally, and I can't off the top of my head think regionally where there were problems, but there are occasionally issues. I guess they were in mountainous areas and up in some higher latitude areas.
All right, and right now I can't see any other questions that are up. Oh wait, here's one from Mike Durand. How accurately can you map zones that experience ephemeral versus seasonal snow cover, given the cloud cover issues?
Yeah, Mike, good. You know, it's a good question. I think we've done a pretty good job. If you look across the U.S., and I might say with this latest mapping efforts of the IMS, they sometimes will use some surface observations to help them as well. And I think they are picking up the inhaling and exhaling of the snowpack over these ephemeral areas pretty darn well. But there still are the issues with the cloud cover. Sometimes they are helped by having animations. It helped immeasurably over the Tibetan Plateau, for instance, to be able to see these clouds put into motion. But it's a challenge. There's no question, because you're dealing with patchier snow. You see the couple examples I showed where an area could look very different under a patchier snow cover than a fresh snowpack. So it certainly poses a challenge. But of course, that challenge is found everywhere in the northern hemisphere at one time or another during the onset of snow cover and the melt back of snow cover in the spring. So no place is immune to having concerns over whether you're able to track the snow or not. We've also gained some confidence over the years. We had seen some areas of huge increases of snow cover, of multiple million square kilometers in a week. And we wondered if it was just a function of suddenly the clouds disappeared and we saw the new snow that had been accumulating over multiple days. But when we looked at this, and this is a paper I did with Dan Leathers from the University of Delaware, we did some work on this, we found that those jumps in snow extent were in lockstep with major storm systems coming across, this was in North America, across the North American continent during the fall season, where you within several days' time can drop a couple of million square kilometers of snow. So that gave us confidence that this mapping was doing a quite an adequate job.
All right, thanks very much. So I think I don't see any other questions on the list. So thanks very much, David. This is a great seminar.
It's been my pleasure. And again, thanks for everyone for sticking with it on a Friday afternoon.
And I just want to say thank you to David and thank you to everyone for coming. This is our last seminar in the series, so we're done with snow. Maybe that means we have more sunny days ahead as we get into spring. And if you're interested in more work from the snow community, we will be posting things on the website that Matthew Sturm mentioned in the very first talk is SWGR. If you Google Snow Working Group, you should be able to find more information, and we're hoping to get more snow educational activities going, including a snow school this summer. Thank you very much. And thank you to Emily from CoASI for hosting all these seminars as well.
Well, thanks, Jessica, but you really pulled it together. And I also, for anyone who's still listening, just want to say that we host these every semester, and every semester we have a host who invites speakers, and we work with them to put it together. So if you'd like to nominate yourself, please talk to me. And thank you.